All right, guys. Looks like it is just reaching our start time. So, a pretty full agenda here today. So, let's go ahead and get started. First, let me know if anyone has any trouble hearing me. But preparing for the storm. Identify and mitigate common architecture and configuration issues, coordinate broadcasts to our impact your operations. So, quick intro. I am Ryan Wortman. I'm the SecOps manager for Grid Security. I've been in IT for just a little bit under 20 years now. I've been Grid Security for about 3 years. Broad enterprise background. I've worked in operations, manufacturing environments. Really a little bit of everything in IT at some point or another. And I am based just outside of Las Cruces, New Mexico. So know a little bit about Sunshine. So you may be asking yourself what this webinar was about networking, broadcast storms. Why are we talking to a cybersecurity guy and looking at this CIA triad about information security? Don't worry, you are in the right place. Just would like to quickly mention the CIA triad, which stands for confidentiality, integrity, and availability. And the CIA triad is a foundational principle in information security. It states that we should protect the confidentiality of information, make sure no one accesses it, should not, the integrity, making sure that unauthorized changes are not made to data, and really most importantly for our operational environments, make sure the data is available when we need it. So at the end of the day, all of the confidentiality and integrity is not useful if the data is not available when you need it. So when we shift to talking about OT environments, that availability really becomes the major focus area for your environments. And I find it's always good practice to meet. So we're going to focus mainly on the A in the CIA triad here, but I'd like to show you how robust network architecture, segmentation, planning, careful hardware selection, all of those things don't just improve our security posture and our security results, they can help us improve the stability and resiliency of our operational environments. So just keep in mind that we don't see security and availability as at odds. We see them as complementary. So our goal here today is to help you get a high-level understanding of broadcast storms, the protocols used to prevent broadcast storms, and show you a bit about how the protection can mitigate their impact. We're not here to go into all the details on how to configure them and really in-depth technical coverage. There's whole courses out there for that. You'll see even Cisco, for example, covers spanning tree protocol from their lowest certifications all the way up through the CCIE. So there's a lot of depth there. The intent today is to give you the conceptual understanding to recognize when problems you're seeing could be broadcast storms and understand approaches for resolving or mitigating its problems. And then, whether it's an outage call, real live troubleshooting, or planning for changes to your environment or maintenance operations, it'll give you the ability to engage with vendors and engineers, talk about hardware capabilities, architectures, and test plans. And that's because in my experience, specific conversations like this are far more productive than general ones like, why is the network always having problems? So that's kind of what we're going to go over today. We're going to lead with this sample site architecture. So before we chat about broadcast storms, let's get a basic understanding of how our sample site here is architected. This is all a lot easier when we have visual aids. So at a high level, A PV site or renewable site is typically architected something like this. You'll have at the top a pair of HA firewalls with connected to redundant ISPs. And oops, it's like my pen's not working. Try that again. You'll usually find that you've got two ISPs, redundant ISPs, connected to an edge firewall in a high availability configuration. At the top here, you'll see that you have redundant root switches, core switches. We'll use those terms interchangeably today. And you'll find the SCADA system is usually connected back up to those root switches. Might be a physical SCADA system, might be a virtualized one. Either way, should have connectivity back to both root switches. And then you will also see fiber connections down here, the orange lines, out into your field loops and field enclosures. And that'll be loop topology with one end of each loop terminating at each of the core switches here. So same thing for both loop 1 and 2 of our edges. The most important thing to know for our discussion today is the loop architecture. Loops are often the root cause of our broadcast storms. And usually when most sites will see you'll have more than one. So we've got 2 on our sample architecture here, but I've seen 5 or more loops, 12 or more switches per loops. The real thing to know there is that means that you can have a lot of these inter switch links and a lot of switches. So that also means lots of links to track and lots of potential redundant paths. So this design is often chosen to the existing physical paths when they are constructing the site, and also the good redundancy allowed. You'll see that really you can lose one of just about anything in this architecture and have an active backup for it, available for it. You'll see this diagram on most of the slides, just as a visual aid as we go through, but I'm going to give you pause for a moment here, give you an opportunity to ask questions about physical topology before we dive in. All right, perfect. If we don't have anything in the chat yet, I'm going to go ahead and continue on. So you'll hear me repeat this a few times. If you take nothing else from this webinar today, prevention is the best medicine. So positive results start with setting a good technical specification for your EPC and SCADA integrator to design against. Then you need to ensure that a networking expert, whether it's internal, external, but a networking expert performs a thorough architectural review before approving the design for construction, procuring equipment, and configuring it. One moment here, I apologize, guys. Still fighting with some audio issues over
here. I was just checking in the chat to make sure that it sounded more clear for everyone. Sounds good on my end and a couple other people's, but I saw some more messages in the chat, so I was just wanting to check if it is better. I think it was, though, so you can keep going. Yeah. Okay.
All right. So, again, please do let me know if any audio problems, and I'll do my best to speak up here. Perform architecture reviews as early in the process as possible. Just a very strong recommendation. And it's not that we don't trust the groups, the EPCs, the SCADA integrators that are building these sites. It's that those reliable and efficient operations are more easily achievable when all of the major stakeholders have a clear understanding of the design and any potential trade-offs that were made and maybe accounted for in design decisions. So if all you get is a physical diagram, looks something like this, or like a single line diagram, you're probably going to want to dig in a little bit deeper before you accept those drawings. Just engage a networking expert, make sure you understand the logical topology as well. So, to better understand storms, let's first do a high-level definition of the types of network traffic. Obviously, broadcast storms or broadcast traffic, but it helps to know what all the different types are as well. So, unicast traffic is traffic that is bound for a single host. To use an analogy, you can think of it like a letter sent to a single address. Multicast traffic is usually not used quite as much in OT environments, and we don't need to talk about it much today, but you can think of it like a magazine or a newspaper subscription. It's traffic that's bound for multiple subscribed hosts. And broadcast traffic is really more like a flyer that goes to every mailbox, right? So it is traffic that is bound for all hosts inside the network segment. And we'll get into network segments in just a moment, but really it's, think of it as a subnet. So it's generally used for things like network discovery, what network am I on, who's my gateway, network management, things like spanning tree protocols, neighbor protocols, and things of that nature, or client requests when they need to know who somebody else is, that's a request, or they need an IP address of their own, like DHCP. So at any point here, if you guys need some clarification, just drop it in the chat. But continuing on. So what is a broadcast storm? Broadcast storm is when broadcast traffic bound for everyone, consumes all resources on a network segment. This generally occurs when there's multiple redundant paths through a network, such as the field loops and our sample architecture. That device sends a broadcast packet out one link and then receives that same packet back on another link. Devices, the network devices, the switches will loop through that traffic over and over again until links become totally overwhelmed and no other network traffic can get through. So hopefully this animation helps visualize it a little bit, but it also helps me to talk through a little bit how a switch operates, a network switch operates. So really it just receives a broadcast packet on one port and it sends that back out every other port, floods it back out every other port except the port it was received on. So when you've got that redundant path through your network, like the link between switch 2 and 3, switch 2 can be reached via either of these interfaces here, right? You can quickly end up with a lot of copies of those broadcast traffic by the same thing arriving paths and sending back out that path. So really short story is in networks, loops are bad. If you have a loop without something that can handle blocking any redundant paths, you end up with broadcast storms. But fortunately, there's controls that allow us to have these redundant paths through our network to provide that high availability without causing storms. These are known as spanning tree protocols, and we'll lead to those on the next slide here. So, spanning protocols are protocols for preventing network loops, broadcast loops like we showed in that last slide by blocking redundant paths in the network. So they do this by calculating the network topology, determining the most efficient paths through the network. They continuously monitor all of these paths and block or unblock links in the event of changes. For example, a link going up and Some example protocols are STP, which is just really the original protocol, the legacy, we call it spanning tree protocol. Rapid spanning tree, which improves on the STP by adding some different type of aging controls. Multiple spanning tree, which is essentially being able to run multiple instances of spanning tree on different networks. And then there's some other proprietary protocols out there that do some similar things like rep, hiring, turbo chain. We're not going to go into those too much today. And we don't really need to understand each of these spanning tree protocols in depth because generally they all work in fairly similar ways. All of your network switches participate in the spanning tree protocol by sending out a special packet that's called a BPDU on pre-configured timers. So you can see what a BPDU looks like down here at the bottom. You don't need to know what every little bit of this means, but broadly speaking, it contains information about the switch that sent the broadcast packet out to other switches, which priority, the cost of the packet traversing the network, and some other operational info, such as what type of message it is, like is it a topology change notification. Again, these are sent out on regular intervals or when links go up and down, topology changes. And yeah, that's typically when they get sent out. So anytime anything changes in the environment, root bridge change also. So when these changes do happen, it'll trigger what is called reconvergence. And so think of like, hey, we initially started with this link over here blocking, and somebody shuts down this field switch over here. Well, unless that link comes back up, this field switch over here is not going to be reachable. So spanning tree will detect that and then allow this link here to come back online. And then when this link on the left recovers, it'll switch this one back to a blocking state. So it just prevents those loops every time, and the interfaces are not up and down. But we call that process of agreeing what their best path through the network is reconvergence. And it's basically just this spanning tree environment reaching consensus on the best paths back to the what's called the root bridge, which will be up here at the top.
You got a question in the chat. It said, are there any type of logical controls that you can implement to address a bad physical design? Something to prevent or limit a high volume of multicast and or broadcast traffic, etc.
There is, and we'll get to that actually on a later slide. So I'm going to just kind of spin through the common misconfigurations we see, and I'll get to it in just a few slides here. So this slide is really kind of more of a cheat sheet or a table of contents. Don't worry if all this doesn't make sense yet. We're just going to span through them really fast and then dig through in more detail as we go through the webinar today. But leaving spanning tree protocols at their default setting. It's common we see these have not been adjusted at all. They do need to be tuned to your environment. Spanning tree is not magic, and you can't let it work as magic. You should make some conscious decisions there. We also see limited mitigation controls for storm events. So whether it's due to lack of hardware support or the configuration just isn't done, it's common that there are no mitigating controls in place to limit the impact of broadcast storm events. Like I said, we'll do those in a second. Limited or no understanding of what your states are. So this looks good on paper. But does that mean that it performs well when you actually do your operation tasks? How does it respond, your environment respond to various failures? What's going to happen when you say de-energize the skid or lose a portion of the site, lose links? You do need to test that. Limited or no monitoring. So it can be very difficult to discover broadcast storms before they actually start causing equipment to lock up. If you're not doing some type of monitoring, usually your first indication of a broadcast storm is going to be things going offline. And then suboptimal architecture choices. Network loops that are too large flat networks do not respond well to broadcast storms. They do not respond well to topology changes, spanning tree reconvergence more slowly, and some poor hardware selection. So switches that don't support any kind of mitigation, only support legacy spanning tree, only support single spanning tree instance, can't configure primers priority. All of these can cause issues. The issues tend to be worse as your environment gets larger as well. And again, just quick cheat sheet again. Mitigations, what can you do? For new networks, obviously, plan ahead, planning, validation, testing before go live, review your design, validate the performance as expected, review your hardware choices, make sure they meet your design's requirements. But as we all know here, not everything's a nice new greenfield deployment, right? You have to deal with keeping the things that are already in operations running. So we're going to go through a bunch of changes you might be able to make to a running environment. I do want to just quick disclaimer, keep in mind these changes, other than just doing more monitoring, do carry some availability risk. They will likely cause short-term downtime if done well, but if mistakes happen, it could extend as far as full site outages, depending on your specific architecture and the level of the misconfiguration. So new and existing networks, there's some more things we can do here. Just make sure you understand your topology and the effect maintenance will have on operations. What's going to happen when you de-energize a portion of the field? What's going to happen when you restart one switch? Make sure you have configured your root bridges. This is the switch that manages spanning tree. Make sure you configure it. Make sure you know what it is and that it fails predictably. And then this is one of the mitigations we were talking about, configure storm control or rate limiting. This can be the difference between really a ticket with the network team to investigate some bad behavior versus like full site outages and trouble. So I really would recommend that as a great mitigating step. Also, make sure you have not left your STP or STP, MST timers based at those defaults I mentioned earlier. Configure the timers based on your site topology. Spanning tree is not magic. Monitor your link state and utilization. Catch these issues before they are outages. Catch high broadcast traffic before it's turned into a bunch of locked up field devices. And set up your log forwarding anywhere it is supported. The vast majority of network devices lose their logs when they are agreed. So send your logs to a central server, syslog server, receive, Splunk, Graylog, whatever that may be. This way you have a record of things, an indelible record of things like topology changes. And bonus, this is also really a great first step for your security logging. But on to the details. I'm going to alternate between these things on a list that you can do at new sites and things we can do everywhere, just so we can get through the terminology as we're going. But it'll always be listed right at the top of the slide, whether it's more applicable to the new site or all sites. And we're going to start with the new sites because probably should hear this a few times today. Prevention in the form of good architecture is the best cure and comes with lots of other benefits. So, new sites. Optimize your network architecture. Generally, when we say optimal network architecture, when you're talking to whether it's security folks or network folks, that means implementing good network segmentation. Divide a network into multiple smaller networks. These are also known as subnets. And we achieve that through VLANs. So, as an example, a simple network might include the following subnets based on physical location or function role. SCADA network up at the top here to contain usually your SCADA devices, historian, etc. An admin that contains things that you're using, like maybe your supplementary servers, interfaces under root switches, and then physical location, in this case, like field loops. So what does this architecture bias in terms of protecting our sites from broadcast storms, making things more resilient? So the first thing is isolation problems. Remember, we said broadcast packets only go out to things that are in their same subnet, in their same network segment. So network problems like broadcast storms are often contained to the network segment when they occur. If you have a failing device out here on the field somewhere and it starts spewing out bad broadcast traffic, if you've implemented network segmentation, it can't extend past here. Your other field loop is safe from that broadcast storm. Your other networks can continue to operate normally. And the other point is that in the context of spanning tree and broadcast domains, when a network link goes down, the whole network segment has to recalculate its best path back to your bridge. So again, if it doesn't have as many links, one of the things inside its loop to calculate reconvergence, and that calculation will happen faster. Smaller networks recover faster due to fewer possible paths and lower chances of indirect downstream failures or cascading topology failures when things are changing while it's still recalculating. Something we can do for all sites is understand your topology. Make sure you've reviewed your documentation, understood it, know what your healthy states are, and your failure states are well understood. Make sure you know your spanning tree topology. So do you have a broadcast domain that covers your entire field? Do you have one for each loop? Make sure you know and document what each of your VLANs is actually used for. And then make sure you know, test failure states and reconvergence times. So how long does it take for things to recover? We have a root switch failure, power cycle, and enclosure. You shut down the trunk interface. Document how long these things take. It's not easy to predict reconvergence times. They'll vary based on the spanning tree protocol you're using, based on your specific topology, which link fails, timers, et cetera, et cetera. So I can't tell you exactly how long it's going to take. Ideally, it should be somewhere between a few seconds and a minute, but what I can say is if you're finding it's taking 10 or 20 minutes before you're seeing traffic restored in the event of like a root switch failure or field switch being powered down, you need to look at your spanning tree topology, you need to review your configuration. Another thing we can do at all sites is make sure you configure your root bridge. The root bridge is the switch that manages a spanning tree instance. So, we've got our field loop over here. If it's got its own instance, the root switch will control the winning topology in that instance. And it's also the central point to which all the calculations are performed. So that's why you want it to be centrally located. It's usually going to be the thing with the shortest number of network links to hop across to calculate. So you'll get better performance out of it if it's somewhere centrally located, like your root switch. So what should be the root bridge? Really, it's almost always going to be core switches. It's the most centrally located. It's the most reliable, most powerful switch in your environment. And it's usually where those fiber loops terminate. So, lowest number of physical links to hop to reach the bridge. They're also usually in substations or central cabinets with reliable power. They often have multiple power supplies, and hopefully your OT team, your on-site team isn't going to shut off your core switches or your root switches without telling you about it. That may not be the case out in the field, of course, but how do you control the root bridge? So the root bridge is controlled through setting what's called the root bridge priority. The lowest priority is always going to win. Bridge priorities are set in multiples of 49, 4096, 4096, from 0 to 6,535. The lowest priority wins. And if you have not set a priority, like for example, the default I think is 32,768, if you've not set anything else, the root bridge is going to end up being auto-calculated by the MAC address. And that means the device with the lowest MAC address is going to win the root bridge if you have not modified your root bridge priorities. The lowest MAC address, a lot of times it's going to mean one, it's a random device, but two, it's a lot of times going to be one of the oldest devices in your network because manufacturers tend to assign MAC addresses sequentially, with the older switches having lower MAC addresses and the newer ones having higher MAC addresses. So make sure you set your priorities. I would recommend that you use 4096 for whatever you want to be your primary root bridge and 8192 for whatever you want to be your secondary root bridge. And this is so that at any point, if you need to, you can actually come in and set something else up with the root bridge priority of 0 and override the existing root bridges if something goes wrong or you need to replace hardware. But also do make sure you set your secondary root bridge. This can provide faster reconvergence in the event of a failure of that primary root bridge because everybody already knows that something has this 8192 priority. So there's no question of what the next root bridge is if you've actually set that priority. It promotes consensus. Conflicts where switches out in the field or still reading MAC addresses trying to figure out, who's better to just set the priority. So something else we can do at new sites or we were replacing hardware really too is spend a lot of time selecting the right hardware for your core switches. Make sure you understand how they handle spanning tree loops, prevention, and how they interact in a multi-vendor environment. Some of these switches only have basically a checkbox to say turn loop control on or off. That's not what you're looking for. What you really are wanting is to see things like, supports multiple spanning tree protocol. Some type of pro VLAN spanning tree protocol. This, again, becomes more important once you get over a few loops or about 50 links. And as we discussed, this is important because topology changes are defined and propagate to all switches in a network segment. So if you only have one spanning tree instance, you don't really have any options. You have to span it across the whole environment. It starts to cause problems over those 50 links, those few loop topologies. So if your environment matches that description, most new builds do, make sure your core switch can support some kind of multiple spanning trees instances so you can take advantage of network segments to break up your spanning tree domains. Also, make sure they support root bridge priority settings. This is so you can, again, define the core or root switches as root bridge. Just want to be able to ensure it's predictable, you know what it is, you can control it. Also, make sure I've seen some switches where they only support setting the priority and nothing else. You really want to see the max age or max hops timers as configurable. This is so you can tune spanning tree based on your environment. So the max age or max hop settings are going to be different depending on your physical topology. Again, you might have 6 links out here in this field loop, or you might have 8 or 10, right? And those are going to be a different number of max hops back to the branch when they're going to take a different amount of time to propagate through the environment. So really you want to tune that to your specific physical topology, and the bridge switches need to be able to support that. And this gets back to your question earlier. I apologize, I didn't catch who asked it, but storm control or rate limiting support. At the end of the day, broadcast storms can't actually be 100% prevented. There's always a chance something causes one, whether it's loop or bad equipment. But if your switch supports storm control or rate limiting, you can limit that impact. These features essentially allow you to limit the number of broadcast packets that are transmitted and keep them from consuming all of it. We'll go into those in more detail in just a second here. And I would also say just a kind of a parting word of caution on this, on your hardware selection. Be careful with proprietary solutions. STP, RSCP, MST, all these spanning tree protocols we've talked about have been around for decades in the IT industry. They're widely supported. Interoperability and backwards compatibility are well defined, well understood across many industries. Experts' advice are very easy to come by. Some of the proprietary solutions, rep comes to mind, maybe high-rate or turbo chain 2, can provide some easy setup or better convergence times in some specific failure states. Just keep in mind that you may be exposing yourself to a little bit of additional risk there. That risk can come in the form of supply chain risk when you need to replace hardware. Could come in the form of a vendor discontinuing support. It could come in the form of just getting locked into a specific vendor. Not saying those proprietary solutions are bad, just make that choice consciously and understand that it often means you have to run your whole network on that one vendor and all the risks that come with that. Yep. Okay. So a little more on storm control and rate limiting, so limiting the impact of broadcast storms may occur. First, let's chat about rate limiting a little. It is a somewhat coarse passive control when you're looking to prevent broadcast storms, but it is setting an upper limit on the amount of broadcast traffic that can be, the percentage of a link, for example, that can be used for broadcast traffic. So as an example, you might have 100 megabits per second link out here to your field. And maybe you'd say only 5 megabits of that traffic can be broadcast traffic, and past that, drop it. And storm control allows you to do some similar things. It's more of an active feature versus a passive one, though. So it protects the network from broadcast, multicast, or even unknown unicast storms. And it does this by monitoring and detecting when traffic exceeds a configured threshold. Same thing, like 5 megabits of broadcast traffic, 10 megabits of multicast traffic. And when it detects something crossing that threshold, it performs an action like disabling the offending port, or it can still take rate limiting type of action as well. But whether it's storm control or rate limiting, both can prevent broadcast storm from turning into a full site outage by reserving some portion of your links, some portion of your available bandwidth for unicast traffic. So that might mean no outage, or it just might mean that, hey, your network engineer can still get to your management interfaces on these switches to do some troubleshooting and figure out what's going on, versus having half of your field equipment lock up, having to trouble somebody out there to start power cycling devices. So good practice to configure these controls if they are supported on your hardware. And kind of our last one for today is applicable to really all sites, monitoring your devices. And there's a saying I like, and it's that monitoring is the forgotten layer of high availability. And really what that means is if you don't catch, when this link fails with some type of monitoring, the way you're likely to know that it failed is by this other link over here failing. That's obviously not an ideal state. You want to catch that first failure. So make sure you are monitoring. And when we talk about network monitoring, we always mean SNMP monitoring. So that should be the support you look for. But make sure you're monitoring your switch state, your core switches especially. Make sure these core switches are up, they're functioning, and take some kind of active alert when they are not. That might mean watching just to make sure it's responding to management traffic, but it may mean things that are more specific based on your specific hardware choices, like is the redundant power supply up? Are the processors and memory saturated? Are links, in a good, healthy state? You'll also want to know that these high availability links everywhere are functioning. Monitor those. Again, all the redundancy does not help if you don't catch the first failure. Monitoring also makes it a lot easier to catch things like what we would call flapping links, so a link going up and down over and over again. It's hard to catch that just by logging into a switch interface and looking at it. It's a lot easier for your monitoring to say, hey, I saw that go down for 30 seconds and come back up. Every one of those link state changes is going to trigger that topology change. That topology change is going to cause outages while it's occurring, and while it's reconverging, and really a lot easier to catch that with good monitoring. And then the last thing I want to point out in the context of broadcast storage is make sure you're monitoring your link utilization. So, like we've talked about, OT devices do not like broadcast storms. They don't like, having 100% of their network interface consumed by broadcast traffic that they need to respond to. If you catch high utilization early, you can take some kind of action before that broadcast storm starts locking things up. Such as unplugging failing hardware, shutting down network interfaces. That type of action is more effective the earlier you catch the high broadcast traffic. So if you see 20% broadcast traffic utilization, maybe you want to go ahead and have somebody check that out. Yep. And thanks again, everybody. Again, I hope you found this valuable and you can apply these concepts to your existing networks, your projects. As Tori said, we love your feedback. I also like to know if the content we share is at the right technical level. Would you be interested in more webinars about broadcast traffic specifically, or exploring how the architectures we discussed can enhance your visibility, improve your security outcomes, et cetera, let us know. But like Tori said, if you need further assistance, whether it's design review, technical services, don't hesitate to reach out. BD Group or gridsec.com/contact. Thanks again.